So I decided to make this final lecture for GIS 201 a video lecture that you could watch when it's convenient for you, so we'll have more time in class to talk about things, work on projects, etc. What is metadata? It's information about a data set. Plain and simple. Helps you understand how to use things and how to apply data properly. It contains information on structure and meaning. It cites the sources and credits for the data. It describes all the access and use constraints, what you can and cannot do. A lot of times it's stored with the data, but sometimes it's stored separately. Sometimes when you download the data you get it, sometimes you have to download it separately. It just depends. Metadata contains information that people need to understand data quality. It should be provided with every data set, and it can be useful or helpful even if it's just data that's going to be consumed in-house. So here are some examples of what something like this would look like. All kinds of information there that's provided. Talk a little bit about metadata standards, but we're not going to dwell on these topics too entirely much. First is the FGDC, or the Federal Geographic Data Committee. They define and manage standards for metadata. They define standard content and format so that it can be shared across platforms. This is incredibly important because it allows metadata to be formatted for one software and still be accessible in another software. You can check out these PDFs if you want to learn more about it. So why do we have to have a standard? Well, if you don't have a standard, it's really difficult to work across platforms and between people and across softwares. Having a standard allows you to share metadata. It provides a single format that everyone has agreed to, that we can all use, and it's defined by the type of information that's needed for most of the data sets. What standards are we talking about? The U.S. federal standards, the content standards for digital geospatial metadata, the CSDGM. There's also international standards as well. The primary purpose of metadata is to document original sources of data, to document the circumstances where the data was put together and how it was processed, to provide a lasting document of the characteristics of the data so that users can evaluate it to determine if it is in fact useful for their circumstance. Talk a little bit about data quality issues next. Data is rarely perfect, but there is no absolute standards. Quality is defined as the fitness of a data set for a particular purpose. So some data that works perfectly for one thing is completely inadequate for something else. As a user, it's your obligation, both ethically and legally, to determine if the data is good enough for what you intend to use it for. There are 6 data quality issues that we're going to talk about a little bit. Lineage, positional accuracy, attribute accuracy, logical consistency, completeness, and temporal accuracy. Lineage is the original source of the data. In other words, where did it come from? What did they do to it? How is it cited? Source and scale. Source scale and display scale. There's sort of an inherent scale with all data sources, but it's not always the same. And so depending on what data scale depending on the scale of data that you use to create something can greatly impact how that data should be considered or used. Here's an example of source scale. You've got these polygons depicting a coastline. At different scales you get very different borders. To find the source scale, usually it's documented in the metadata, the scale of the original paper map source, or the scale of precision that the data was gathered. It's typically in there, and it's an important element. When we talk about lineage, we're talking about the process steps. Each process step from the source to the final product is listed. What step was performed, who did it, when was it, if you made changes, or the transformational errors, or the root mean square errors, and what software was used. Here are some examples of what that would look like. Positional accuracy is an assessment of how closely features in the data set correspond to the actual positions in the real world. In other words, when you have a line representing a road, does the road and the line occupy the same space? Does this line follow the road? That's positional accuracy. Are things where they're supposed to be? Geometric accuracy is a little bit different. Is something where it says it is. It's level of error in the original source. Additional errors included that can be propagated during data processing or examples of that. Precision has to do with the number of significant digits in a measure. It's the statistical variability of a repeated measurement. It's not the same thing as accuracy. It's when you measure something and then you measure it again and again and again, and we assess precision by the variability in those repeated measures. Scale and precision. The main things here I want you to keep track of, or at least understand, is a 1 inch equals 72 points, and so a 3-point line. If you work all that through on a map that's 1 to 100,000 scale, you can see how one line there could be 347 feet for a 3-point line. That's at resolution. That's at scale. So think about that. National map accuracy standards. Base data developers follow stringent quality assurances and control procedures when they produce base maps. The national map standards specify procedures and quality guidelines for testing the accuracy of maps. There's like at least 20 checkpoints, and there's all the different stuff that they got to do to make sure that when they generate these products that they are in fact good quality. In practice, maps are rarely actually tested to see how accurate they are. What you can assume is that the quality base map products from organizations like the USGS and the National Map conform to the standards of the National Map Accuracy Standard. Some general rules of thumb: if you assume a typical line is a 0.5 millimeter wide, a map scale divided by 2,000 gives you the approximate precision in meters. So a line on a 1 to 5,000 map is about 2.5 meters. A 1 to 1 million, it's 500 meters. Remotely sensed data is its own unique sack full of cats. Accuracy varies depending on a lot of things. What was the resolution of the original instrument that captured the data? How much geometric correction had to be applied to it? Was it resampled after it was captured? What's the cell resolution provided a minimum estimate of accuracy, although it could be a lot worse? So if you know something's at 3 meters, you assume that it's accurate to 3 meters, but that is not always the case. When we process data, some of the things we do can degrade the quality. Think of rectifying images and how that changes the appearance of the image. Will be an example. Root mean square error is the relative difference when we georeference things. Understand that it doesn't necessarily mean you do have a good fit just because you got a good RMS. That is contingent on having your data points spread evenly across your study area, and that you have an adequate number of points. We can also use tolerances when we intersect things as a way of working on stuff that can reduce slivers by setting our XY tolerances. You make them too low, they don't stop anything. You make them too big, and you lose information. Attribute accuracy is something entirely different. To this point, we've kind of talked about the shape geometries and distances and positions of where things are located and that sort of stuff. Attribute accuracy is how well the attributes of something are corresponding to reality. These can be very complex. And it can be problematic because a lot of times there's no good way to assess how accurate or inaccurate they are. Thematic accuracy is a variation of this theme. How accurate are attributes that relate to the theme or the concept of what the data is. Things like tree crown density, how is it measured, how accurate are the measurements, what are the sources of error, how much error is there, that sort of stuff. Measurement errors. Precision and accuracy of the instrumentation that's used to record the data is a GPS unit where you're trying to get elevation data with LiDAR and heavy forest canopy. How did you measure the phenomena? In other words, if you have like a geological contact, was it something that's visible or you just assumed it to be there? Just like with census data, was it something that was counted or was it something that was estimated? How homogeneous is the measurement over the measured area? Some properties change dramatically in very short order, others are very stable across larger geographic areas. Understanding all of these can impact how much error occurs. Classification issues, again, you should know by now how you classify your data has the potential to influence how people interpret your data. If you do it purposely with malfeasance at heart, you could create a classification scheme that in effect makes the data appear to say one thing when it in fact should say something else. Basic good old-fashioned mistakes. Screw-ups happen. When they happen, stuff gets jacked up, doesn't work right, things are transcribed wrong, they're entered incorrectly, someone left a minus sign out, someone put all the X's in the Y's and all the Y's in the X's, and sometimes people just do things wrong, like they call a hayfield a cornfield because it's flat and square. These are mistakes that happen. How do you assess these? Usually you got to have a lot of background knowledge of what's going on, detailed information. You need to understand how the data was collected, the instrumentation characteristics, how it was processed, what are the general professional practices related to that, and how different was this data from what is considered standard. This can be challenging, and it's okay not to know if you really don't know. Logical consistency describes how well features mimic the real-world situations, usually confined to testing for topological errors. In other words, things are supposed to respond and react in GIS the same way they do in the real world, and so we look for things that don't quite line up, like undershots and overshots, improper intersections, pseudonodes, loops, gaps, and overlaps, and all these other various things that occur when we don't properly edit stuff. Topology rules are established by how features should be spatially related. It's essentially telling the data structure that things like coincident boundaries between various counties like Shannon and Bennett should have the same line. It should not be two lines, it should be one line. That is the border or the boundary of each individual area. Here are some examples of what happens when that's not the case. Data quality, there's lots of things about that there. You can see here a report on logical consistency talking about the types of errors and problems and things that occurred, as well as other things. Completeness is important. Completeness assesses whether a data set captured every known instance of a set of real-world objects. All the original data are carried through to the final product. So if you know something is there in the beginning, is it there in the end? Did it make the final cut? Polygons are all areas of the map covered. What's the smallest wetland mapped would be an example one to see if it actually shows up. With lines and points, did the dot map every single road, or in intermittent and perennial streams included? These are the kind of things that you have to consider when we talk about completeness. If you have a stream network, does it literally have all the streams? Here are some examples of a completeness report for earthquakes and one for digital line graphs. You can go back into the slide set and read these at your leisure. Temporal accuracy is another problem. It assesses how all information at the time of production still represents the current ground conditions. So think of this as how has reality changed since the time when the data was actually converted or created. So let's talk a little bit about the different scales of change within data. Virtually invariant are things like geological maps and digital elevation models. They're pretty much intact and don't change. Other data takes decades to change. Things like land use and vegetation maps and earthquake maps, those sorts of things tend to be fairly stable. Other things change on a much more dramatic time frame, like census data, or whether an area is experiencing drought or crop production. These typically change yearly. Then there are ephemeral, or things that change really rapidly. Think of radar images of storm fronts moving through, or daily temperatures. Updates geospatial metadata that measure variant phenomena should include information about the currentness of the data. In other words, how close to now is this data? Update frequency. How often do we do it? Is there planned intervals that we go back and look at this stuff? Or is it never updated? We're going to look a little bit at the format of metadata next. There are 7 basic sections in metadata, main sections. They vary somewhat from standard to standard, but in general, it's identification, data quality, spatial data organization, spatial reference, entities and attributes, distribution information, and then the metadata reference itself. So what are these things? Identification is basic information such as title, where it's located at, any keywords, any rules for acquiring it and using it, that kind of stuff. Data quality is the assessment of the positional and attribute accuracy, completeness, and the consistency, and just all those things that tell us how good the data is. Data organization is how the data is organized or formatted. Is it raster, is it vector, etc. Spatial reference is all those properties that we learned about through the course of this and your previous classes that include but are not limited to your projection, the datum that the particular data was created in, the extents in terms of your maximum x and your minimum x and your maximum y and x and minimum y values that you have, and that sort of stuff. It also has some information about the content of attributes and stuff, and this can be really helpful because it can explain abbreviations and codes and the column headers, if you will, in some data sets that may not make a lot of sense, because it might say, this is E0026, and you don't know what that means. But when you look into the metadata, you can find out exactly what that column of data means. There's also distribution information, where you get the data from, who you contact, that kind of stuff. And then the metadata reference, this is information on who created metadata and how it's organized. So we'll kind of look at these a little bit more. Identification, what kind of data is it, where to come from, what's it for, who can use it. Common identification information would look something like this. Here are some key identification terms: abstract, purpose, supplemental information, current references, status, data set credit, citation details, spatial domain, keywords, access constraints, use constraints. These are the kind of things that go into it. And essentially you would use these elements to fully explain what the data is. Data quality, it's all that information. Completeness, logical consistency, positional accuracy. What did you do to the data to make the data layer that you are talking about? Quality information, a lot of this is just basic reporting of what you found out. The key data quality items obviously are these. Data organization. This section contains information on the type of data and how it's stored. The good thing is ArcGIS fills this out automatically. Spatial reference. This contains information on the GCS, the data, and the projection. Again, this is filled out automatically. Entity and attribute section. This section records information about the general data set, overview, or individual attribute fields. It defines what information is in each field, includes codes and abbreviations. This is where you can find things to make sense of what you're seeing when you look at the data or the attribute table. description is used when fields are similar or self-explanatory and can be described together in a paragraph or two. An example would be like if you had a field that was area, you have one that was length, you have one that was type, and you could, in a brief sentence, say that type has to do with the type of road. Area has to do with the size of any whatever's in certain units, and the length is in meters or something like that. And then you could explain it. Detailed explanations is when you have a field like GF6229 and you've got to explain what that actually means. This section provides information on a lot of things: who distributes or sells it, what format it's sent in and distributed in, is there a cost, how do you get it, what can you do with it. This is all in the distribution section. Here's an example of what that would look like. Some of the key things are the distributor, the format, the standard process by which you would request it, and then the available time period. In other words, when people intend to make this available. The metadata reference describes the format of the metadata and who developed it. These format fields are filled out by ArcGIS. And here's an example. The contact who developed the metadata, the format that it was stored, and the distribution restrictions are some of the key metadata reference items. So what do we do when we want to find metadata? How do we acquire it? It's been around for a long time. Tools have not always been there. Not all organizations use it. That's a problem. It's often stored separately. That's also a problem. There's nothing worse than finding really good data but not having metadata so that you don't know if it's really that good after all. Generally, when you download things, you want to look and see if it has metadata with it or if the metadata is downloaded separately. Rule of thumb: don't bother downloading data unless you can find the metadata too. Talk a little bit about metadata development. Development starts when the database development starts. You should collect information along the way that you need to fill this stuff out. Smarter organizations build a process. In other words, they will know in general what they're dealing with data-wise. They will sit down and make templates and examples, and as they do things, they will fill these forms out so that when they get done, they can simply enter that information into their form, and voila, metadata. This will be an example of a metadata note that you would use to do something like that with. So we're going to look at the metadata editor. There's different storage formats. You can store it as text, as an XML, an HTML, all other different kinds of formats. When you look in our catalog, in the description tab, you can see a lot of this information. You can go to ARC catalog options, and under item description, you can change how this is set up, but you can basically tell it to automatically update when metadata is viewed. You can go into the options and you select the different formats you want for your metadata. Once you've looked at the description tab, if the metadata is there, you can expand the things and see what the individual elements are, and then work to edit those individually. You can see there's quite a bit that can be added to these. The big thing is to make metadata that is FGDC compliant. This means that certain fields are required and that all the fields need to be filled out in order to be compliant. If you plan to distribute it, you should fill this out at a minimum so that other people have access to it. Generally, contracts, when you're dealing with data, include FGDC compliant metadata as a condition for completion of the product. In other words, if you're making data products for most federal, state, or local agencies, they require metadata that meets this standard. So this is some comparisons of what these different types have as far as the elements. The North American profile, metadata information has these things, whereas the FGDC has these. Let's look a little bit at the metadata templates. Many fields in metadata are identical for things that organizations would produce, and so there's a lot of duplication of information. And that makes it really important that if you're going to, for example, be working at a firm that generates specific products in a raster format from aerial photos of a specific country, for example, for an intelligence agency, you can develop a template, and much of what would go into the metadata would be the same for all the data that you worked on. This would allow you to save a lot of time by creating these pre-populated templates where you only had to add the things that changed from day to day, from site to site, from tile to tile. An organizational template contains information common to the whole organization, and then the project template contains additional information unique to projects. But it's for the same with the data sets within it. So think of it as a tiered example. You have this big organizational metadata template for certain things, and then within individual projects, you might augment or supplement that template to reflect the things that will be common across that, and then down to individual types of things or sections of data, there might be additional ways that you can standardize things to make less and less work creating the metadata. You're going to have to decide what fields are going to be the same. You might actually just save it as a template. Is one way they're talking about doing it, and so instead of trying to do this the hard way, you create a shapefile that has all the things filled out that you need and simply call it meta template shapefile. And then all you have to do is open up that document and save it as something else and continue working from there. Once you get more familiar with the 7 sections and what goes in them, you know what to start looking for. It makes it a lot easier to create metadata. So when you're going to make metadata, don't delay, start today. That's the motto. It's easier if you plan to do this and you start collecting and saving things as you move along. Much easier than it is if you wait till the very end.